Now volume is done. We have learned all the techniques that we will learn to compute the volume of either a solid with known cross-sectional area or a solid of revolution. On to more topics in geometry. First off, arc length. Before we talk about arc length, we have to define what it means for a function to be smooth. So a smooth function on some closed interval has a derivative that is continuous on that closed interval. And it's called a smooth function because they look like this. All smooth. That's kind of not smooth, but it's all a nice smooth function. Just everything is all nice and swoops and stuff. This is not a smooth function. There's like the sharp points. Sharp points are cusps, and f prime does not exist at those points. So a smooth function has no sharp points, no discontinuities. It's all smooth. And a smooth arc is a piece of some smooth functions graph. So for example, this little piece right here of this graph, that is a smooth arc. It is a piece of a smooth curve. And smooth arcs are the only kind of arcs whose lengths we can find with this next technique. So, how to find arc length. How to find the length of a smooth arc. And by the way, even if a graph isn't totally smooth, you can still find its arc length. Let's say that you had a function that looked like this, and you wanted to find the length of that curve. You would just find the length of this smooth arc, and then add it to the length of this smooth arc. So if either on the p-set or on an exam you want to find the length of an arc that is not completely smooth, you have to break it up into smooth pieces. Find the length of each smooth piece, add them up for your overall answer. Okay, how to do that? How to find the length of a smooth arc. So let's say that we have ourselves some smooth arc like this that goes from like A to B. And our goal is to find how long is that arc. If we were to take that and like straighten it out, how long would that be? Well, the way we do it is we first break our region into a finite number of subintervals. So let's do this. Perfect. Then we find the points on the graph that correspond to each of our subintervals endpoints, like so. And then we use straight lines between each of those points as an approximation. So to find the length of a smooth arc, we approximate it. And just like with area and volume, we approximate it with a shape whose formula we know for this quantity. We know how to find the length of a line, so we can do that. So, the arc length, which by the way, arc length is almost always denoted lowercase s. I hate using s's because they look like fives too often, but arc length is a lowercase s. And the arc length is approximately the sum from 1 to n of, I'll call them L sub I, where L sub I is the length of the ith line. So as I drew it, I have 1, 2, 3, 4, 5 lines. So the arc length is approximately the sum from 1 to 5 of L sub I, the length of the first, second, third, fourth, and fifth. What we need is an expression for L sub I. So let's use one of these as an example. So like here's like the first, second, we'll use this right here. So this one right there is L sub I. Now this is the third line segment, 1, 2, 3. And if you see, if I was to break up my subintervals based on x's. A is x naught, that's x sub 1, x sub 2, x sub 3. The third line segment goes from x2 to x3. In general, the ith line segment it ends at the ith point, and it begins at the I minus 1 point. So again, the third line segment goes from the second to third x values that we use to partition our interval. In general, the ith line segment will go from the I minus 1th to the ith x value. Right? So like the fifth one, for example, went from 4 to 5. The first goes from 0 to 1. So the ith goes from I minus 1 to I. And the length of that line, we know, because it's just the distance formula. It's just the change in x squared plus the change in y squared. And so our sum is all those things. But that's not a Riemann sum yet. Right? If I just did the sum of this, there's no delta x there. So this is not a Riemann sum. If this is not a Riemann sum, I can't use integration for this yet. Like, we need delta x. Because Riemann sums have delta x's. Riemann sums are the only sums that turn into integrals, at least for our definition. So we do a bit of algebra to it. So L sub I is the square root. We factor out x sub I minus x sub I minus 1, because when you think about it, this is delta x. So we need one of these at the end of our expression. So we're going to do some factoring here. We're going to factor that out, and we'll put it at the end of our expression. So we'll have something in there, and then at the end we'll have the x sub I minus x sub I minus 1 squared. When we factor this out of the first term, it gives us 1. When we factor this out of the second, well, factoring is division, so we divide it out of that, and it gives us this expression right here. The change in the function over the change in the x value squared. And if you're unsure if that works, just multiply it back in. When you multiply this back in there, those two cancel out and you're left with what you started with. And since we have the square root of this expression squared, we can then bring it to the outside of the square root. And then times x sub I minus x sub I minus 1, and then that is delta x. So now we have delta x, and so we'll write this again. I'm going to change one more thing too. So two things happen here. The first, or the second change is obvious. That's the change in x. The other change was not so obvious. We replaced this quotient with f prime. Well, when you look at it, this is the average slope of f. And by the mean value theorem, the exact slope will equal the average slope for any continuous and differentiable interval. Since our function is smooth, we know it's continuous and differentiable, therefore the mean value theorem has to apply. And really, I'll put x sub I star, a little star on top, because this isn't guaranteed to be the same x sub I as up there. It's just there's some x sub I star in the ith subinterval where the slope there is the same as the average slope. So if I take the mean value theorem and I rewrite it in terms of i's and I naughts and everything, it'll be f prime of x sub I star is that quotient we just had. This is the exact same as the mean value theorem. It's just written for the ith subinterval. So instead of a and b, you have x sub I minus 1. Instead of c, which is that third point, you have x sub I star, which just means some point in between those 2 points. And so now we have this. This is a Riemann sum, which means the exact arc length is the limit as n goes to infinity of 1 plus f prime of x sub I star squared times delta x. That's a definite integral, so we write it as 1. You could also do it in terms of y. It just depends on what the function's given you. So to recap, arc length s could be in terms of x, integral from a to b of root 1 plus f prime squared, or it could be in terms of y. And the only difference between those two, which I mean to say is the only way that you know which of those to use is what function is given to you. For example, if you were trying to find the arc length of like 3x squared plus x cubed, you'd want to use x. If you're trying to find the arc length of like sine of 3y, you'd want to find y, or use y. So however the function is given to you, that's usually how you choose which of those two techniques to use. Informally, so that was the more formal derivation of the formula with Riemann sums, all that fun stuff. A bit more informally, here's our arc length. You break it up into a bunch of small pieces, just like we did. Right, and what I'm doing here is showing you an informal way to get to the same result. Right, so as you get an infinite number of these points, you can think of each point pair as making a triangle that's insanely small. Right, it's so small. So this is dx and that's dy. That is the differential, right? The change in x and the change in y for these infinitely small changes. And this right here is the change in the hypotenuse, s. And so to get the same exact formula, you just have to realize that s is, for the Pythagorean theorem, dx squared plus dy squared. Factor out a dx squared. And you get the exact same thing, just 1 plus f prime squared dx. So it's the same basic idea because the distance formula is Pythagorean theorem. It just does it a bit quicker, I suppose. But same idea.